Good afternoon, everybody. Welcome back to lecture number 41. So continuing our discussion on the special machines, last time we solved a big and important example in single-phase induction machines. And do you remember what was the key feature about this example? The key feature about the example we did last class is we recall that the torque has this equation, so make sure to include it in the formula sheet. In the final exam, I will go with another suggestion. If a student doesn't want to use the exam formula sheet, he or she should bring his or her own formula sheet. So if you don't like the formula sheet designed by the class, you can use your own, okay? You can use your own. The other equation, if you look at the air gap power, it's additive. So in terms of power consumption, I'm adding the forward and backward. In terms of the output torque, I'm subtracting the forward minus the backward. So let's do this example again one more time. From blocked rotor test, what did we get? We solved using these quantities. This is rated current, this is rated voltage. We solved the equations and we got the equivalent impedance, and then we assumed x1 and x2 prime are equally separated. They are not x-mag, not yet to be found. This is like the stator and the rotor, they have the similar windings. Then from the short circuit test or the no load test, we dropped the forward resistance and the backward admittance because inductance, because this is a function of 2 minus s, this is a function of s, and this is almost like an open circuit, this is almost like an open circuit. And then if you do it, you will get two components. If you solve the equation, you will get R and L. If you get R and L and you do the math, you can solve it to get X magnitude. Once you have X magnitude, R1, R2, and everything else, you can develop the equivalent circuit. So keep in mind, this is half R2 prime, this is half R2 prime, this is X mag, this is X mag, 50 X mag over 2, this is X mag over 2, this is X1, and this is X2 over 2, X2 over 2. Okay? Now, the example that we rushed in the previous class, which I'm going to solve today, and if you have calculators, please open them. It's time to practice. Definitely single phase will come. Definitely. Definitely it will come. It's more important to me than universal step. Because this is the most common machine. This is the one you're going to see in the design, in the expo. This is the most common machine. So for the single phase induction motor of the previous example, find the input current, power factor, developed torque, output power efficiency, air gap power, copper losses, when it's connected to 120 volts supply. So if you connect it to the 120 volt supply, you have to get first the slip, because 120 is rated voltage. If I connect it to rated voltage, I'm going to get rated speed. If you get the rated speed, get the slip, which is 3.9%. Keep in mind, I prefer always to add an additional digit in the exam to get more accurate answer. Then calculate the the Z forward and the Z backward. How do we calculate them? Using this circuit. If you draw the equivalent circuit, so maybe a question in the exam, draw the single phase equivalent circuit. Because I know this single phase equivalent circuit is not the same one for three-phase induction machine. So please, هذا مهم, okay? It's very important to draw the circuit. Okay, so you may include it in the formula sheet, or maybe you will have it with the parameters, maybe something like that. So you have to calculate Z forward and Z backward. The forward, then you can calculate it as the parallel combination between the two. The backward is the parallel combination between the two at rated slip. Rated slip. Then after you find the forward and backward, you can find here what he did is he had to find the input current. This is the first quantity, the input current. Finding the input current is nothing but the input voltage over the equivalent impedance. which is this resistance plus the forward plus this impedance plus this impedance. Okay? Here, that's why we do it here. It's the forward plus backward plus R1, forward plus the backward plus X1. Add everything else. Can you do this using your calculator quickly? Quiz. The real quiz. I'm not talking about the fake quiz. So let's verify. It's 227.86J. Okay. Let's calculate it backward first. How to do it is I would do 1 over 27.86 times J plus 1 over J times 1.63 plus 1.35 over 2 minus 0.035. And then I get a number. This number, take its inverse. It's 1 over Z plus 1 over Z. This is a very good skill. So what did I get? The backward, I got this number, 0.61 plus J 1.55. Probably no need to memorize the equation. I just need to memorize the circuit, how it looks like. If you do the forward, you do the same. 1 over this plus 1 over the summation. The final answer, click X1. Do not waste your time in the exam. The final exam might be a little bit lengthy. Time is important. Okay. Then you add these two with this R1 plus JX1. And then you should verify using calculator. Those who are in the career fair, please make sure you get this number accurately. And usually the angle of the impedance is the angle of the power factor, but let's wait until you get the current. So current is leading, is lagging the voltage because it's minus, so that's why it is 0.61 lagging. Okay? Then how to get the input power? The input power is the supply voltage, 120, times the supply current, times the cosine theta between the voltage and current. Should I multiply by 3? No. For single phase machine, never ever multiply by 3. Okay? Then if you do the input power, you can see from the numbers it is 4.41 times 120 times 0.61, and it is nothing but 322.81. So this is an induction motor. It means any future power calculation, if you multiply by S, the air gap, the forward air gap, the backward air gap, has to be always less than this number. Okay? One common mistake is students usually have answers that are not realistic. Power factor larger than 1. For a motor, synchronous speed for a motor, synchronous speed is smaller than the operating speed. This becomes a generator. Doesn't make any sense. Okay? For the synchronous speed, what's the synchronous speed of the machine? It's 1800 times 2 pi over 60, that's 188 RPM, because we use the torque equal I square over synchronous speed. Now, what if I ask you in the test, calculate the mechanical torque? What's the mechanical torque? You replace omega async with omega mechanical. What is omega mechanical? 2 pi over 60 times the other speed, which is what?
Operating speed.
The operating speed, 730. And the electrical torque for a motor is higher than the mechanical torque. Okay? This is one of the tricks where I want to test the A+ student. Okay?
As a concept?
Probably maybe in the exam.
لا بشكل عام الإلكتريك دائما أكبر من الميكانيكي.
I think a generator is the opposite. For the generator, for a motor, yes. But for a generator, the mechanical input power is always larger. Because you're going to have, the difference would go into friction, windage, الرياح, friction between the bearings, and any other mechanical constraints. One of them is, for example, the center of the inertia of the rotor has to be held during a rotation. And if it's held using the bearings, the friction is with the bearings. Also, making it eccentricity. Do you know what's the eccentricity? Usually for every machine holding the rotor to be exactly in the center, they apply for critical machines, they apply laser, and they study the eccentricity of the machine. If the machine center is not really aligned, maybe slight deviation, this would create vibrations, which would translate into losses. So this is another losses. This is from the miscellaneous losses. But eccentricity is important for very high speed application. I remember when I was doing my grad school, one of the PhD students, he claims to be having a 1 million RPM machine. It's a very small machine, 1 million RPM. And they claim that they break the record. Nobody has done a 1 million. Ultimately, it scattered the machine, 1 million RPM. Clear? So, let's talk about the mechanical torque. It's 1.28 Newton meter. That's a very small number. So the mechanical power, which is the air gap power times, this is the air gap power, so this is PG, times 1 minus S. If you multiply it by 1 minus S, you get 23.87. Maybe the mechanical power will be a little bit slighter, higher. So this is the mechanical power. The output power, and we said last time, this is the mechanical power minus the rotational losses. The rotational losses is found from the previous problem. So the mechanical power is this, minus the rotational power, you get your final output power, which is 158.93. How did we find the rotational losses? From the tests. Rotational losses are usually found from the test, and in the previous example, we found the rotational losses using this example to be from the no-load test minus the copper losses. So if there is no load, if I just subtract the copper losses, this is the copper losses, I get the rotational losses, which is 72.90. This is a very huge. This includes core losses, magnetization, etc. This is if the machine has no load, you're going to lose some power other than the copper. This is how to calculate it. From which test? The no load test, the 125. From the 125. This is the no load test. So no load power is copper losses plus rotational loss. Rotational losses, if you subtract P converted minus rotational losses, you get your final output power. And this is very not efficient machine. If you look at it, your input power is 322. Your output power is 158. That's a 50%. So usually three-phase machines are more efficient. But sometimes you can sacrifice efficiency for small power application. So let's continue. Now he asked about the air gap power. One way to calculate the air gap power is you get this PG multiplied. Well, the problem with it is if it was a three-phase machine, what is the copper? The air gap. The air gap power. What is the air gap power? It is 264.69, which is higher than this number. So you can get it by just getting these two numbers, 188.5 times 1.28. But the question asks you to calculate the forward and the backward. So this, you cannot use the S equations, you have to go back to the formula of the air gap power for forward and backward. And if I'm not mistaken, the forward air gap power has this formula, the backward has this formula. It has I1 square RF, I1 square RB. Okay? Basically rated current times the forward and rated current times the backward. And if you do the math, what do you notice about these two numbers? The forward is larger than the backward. Forward is 252. The backward is 18.6. If you add both of them, they should sum up to this number, 188.5 times 1.28. So when you solve this example, don't just memorize. Understand. Maybe because if I change the order of the questions, I don't want you to be any panic in the exam. Okay? في ورقة؟ ما إذا ما عليك for the attendance. So stepper, okay, then the last question is find the rotor copper losses. What is the rotor copper losses? Rotor copper losses is provided in this formula. What is it? Here. It is SPGF plus 2 minus SPGP. That's the total rotor copper losses. And if you do the calculation, it's going to be a small number. I don't think it's a big number. It's 33.12 watts. So this is one of the questions that was asked. So any question about single phase induction machine? The other type of machines, the last important one from our course. So we talked about the universal. We talked about the single phase. Now we have a very interesting machine. It is also important, called the stepper motor. How many of you have dealt with stepper motor? It's very common. What is the major thing about stepper motor? What is the name step? It moves with steps. It doesn't rotate. It moves and stops. It moves and stops.
It is common in 3D printers.
It's common in 3D printing application. It's common in regular printers. Even the printer, when the printer prints a paper, I'm not talking about the laser printer, the fast. I'm talking about the cheap printers. They rotate, draw a line, rotate, draw another line. So that machine is a stepper machine. And what do you notice about it? It has more poles, and those poles are in a shape that somehow, the stator is not purely rotor, it's salient. It's not rotor. It's not round, it's salient. And also the rotor is salient, so both of them are salient. And if you notice that this is the outside box of them, how they look like. So stepper motors are electromagnetic, incremental devices that convert pulses to shaft motion or rotation. So they work using power electronics by sending different pulses, and then they move only small steps. A very common application is solar trackers. Imagine if you have a solar plant and you have those panels that you need to shift them during the day. Should you bring an induction machine that would rotate?
No.
And then they will move fast? Or should you use a stepper motor? So every panel they have a stepper motor, and if you optimize the cost of stepper motor, then you can reduce the cost of your plant. And this is a very common application. So printers, solar trackers, but stepper motors in solar trackers are big. Yeah. These motors rotate at specific numbers of degrees when we send them a pulse using the microcontroller. Typical angles are 2.5 degrees. So 2 degrees you have a circuit, 2 mechanical. It's going to be like this. 15 degrees, it's going to be like that. Get it? Usually shouldn't exceed 30 degrees, between 1 to 30 degrees, per input of electrical pulse. Position sensors or sensorless feedback based on techniques can be used to regulate the output response according to the input reference command. It is very important to consider that some of those stepper motors, they have closed loop sensors, they usually have Hall effect sensors, or they put, for example, a barcode, and if that barcode completes one rotation, you get one rotation completed. This is one common application. So some of them they do not have. Some of them are sensors, some of them are sensorless. So stepper motor is the digital actuator. It's a corresponding digital motor, machine. Should we have a stepper generator? No. So there are things that doesn't make sense. Stepper generator should not be there, because having a mechanical precise movement is not realistic. It's in the form of programmed energization of the stator winding, and whose output is in the form of discrete angular position. Let me explain to you just how it works. Imagine if we have a 2-pole and then I have a stator that's like that. Imagine if I have a coil here, and I have a coil here, and I connect it to what? Power electronics, PE. Let's say the power electronics sends a pulse. Ultimately, it would say connect this to a DC voltage. I'm not saying AC, DC voltage. At free spin, you can spin it without any issue. Let's say at a random position it was like that. The flux lines without energization, how do they look like? Do I have a permanent magnet? This is one type of stepper motor. Do I have a permanent magnet? No. It's just coils in a steel. Coils wrapped around a steel. So if there is no energization, nothing will happen. Let's say I energize this and that. Am I going to have flux? Yes, I'm going to have a flux lines that would pretty much go through the stator and go here. And another flux line, go here. صح ولا لا? What will happen to those flux lines with this steel? This steel has no coils. It's just a steel. حديد. حديد يمر في مجال مغناطيسي. If it's close enough, it will not rotate. It will align itself and stops and hold. That's it. Who said it will rotate? To rotate, for rotation you need to have RMF. Do I have a rotating magnetic field, or this is a constant magnetic field? حطيت DC supply الفلكس لاين صارت كذا، هل هي constant ولا rotating؟ هل هذه الدائرة قاعدة تدور؟ هل المجال المغناطيسي بالشكل هذا قاعد يدور؟ هل الكرة الأرضية المجال المغناطيسي حقها from north to south هل هو قاعد يدور؟ So the earth is not an RMF. It's tilted a little bit. Every year it tilts a little bit. This is physics, not physics. Astronomy. So this is similar to the earth. The only thing that you would need البوصلة قاعدة تثبت نفسها. That's it. Think of it كأنها بوصلة. It's a needle, steel. So this needle, it's not a needle, it's a rotor. It would align. So at this point, it will rotate and align and hold in this position. And that's it. For a two-pole structure, that's the best you can do. This is what we call them a variable reluctance. It means I'm changing the reluctance of my flux path to align the motor in the structure. And now, because I have PE, now I can have special types of machines that has the capability to align themselves based on the power electronics. We do have switched reluctance, we do have many other things, but stepper motor, it aligns and stops. So what will happen if I add coils here, and de-energize this and energize that, these two? What will happen? If it has enough inertia, that's the key, from the stop, maybe it will align, maybe not. We don't know. But assuming the rotor weight is negligible, it will definitely align here. That's a 90-degree stepper motor. But that's not realistic. How to make it successful? We add maybe 6 or 8. Reduce the angle. Now I can align them. Get it? Can I make it even more precise movement? Yeah, هنا يجي لعبة power electronics. Can I energize 1, 2, and ignore 3?
Yes.
Yes. And we will see this in the stepper motor. This is the simplest stepper motor type, which is called the variable reluctance. This is in a nutshell how stepper motor works. No magnets, no AC, it's just DC with some power electronics to control the transistors.
تختار الانجل depend on the coil, number of coils.
That is not coils, depend on number of salient poles.
دكتور range of speed limited هنا.
It doesn't rotate for rotation. Range of speed from this angle to this angle is usually a function of the weight of the rotor, is how fast you can send the pulses from power electronics. But it doesn't rotate for rotation, so it will not have a full RPM. But moving from this angle to this angle very fast requires very fast power electronics. If the power electronics is slow, it will move and stop. It will move and stop. One common application for stepper motor is watches, electric watches, not mechanical watches. So lots of watches, الساعة تمشي using a stepper motor. It's very crucial. Machines are everywhere. Clear? So let's go over the advantages and disadvantages. One advantage is the rotation angle of the motor is proportional to the input pulse. If the input pulse is fast and sharp, I can control it. The motor has full torque at standstill, even if the windings are energized. One good advantage is that because of this magnetic pull, it can have a higher torque compared to induction. Precise positioning, repeatability of the movement, since good stepper motor have accuracy of 3 to 5% of a step, and this error is non-accumulative. If it misses this alignment, usually this does not propagate to the next alignment. That's why watches are precise, but they become not precise after 3-4 months. So there is error, but it's not accumulative. Excellent response to starting, stopping, reversing. Just do the power electronics game. You can reverse, you can stop, you can hold. So it's good for robotics, for robotic applications. Very reliable. There is no brushes, there is no permanent magnet, there is no bearings. Therefore, their life is long. That's why watches, it's only the battery you have to change. The motor's response to digital impulse pulse provides open loop control, making the controller easy. You don't have to have sensors. If you trust your power electronics, you trust your output. It is possible to achieve very low speed, synchronous speed rotation when it's directly coupled with the shaft. For induction machines, usually there is a gearbox. There is a big gearbox and there is a small gear. So this is big gear, this is a small gear. So here they couple it with the induction machine or synchronous machine or DC machine. And then the axis of rotation, again, you're going to get a smaller speed as the radius is bigger. But for stepper, you don't need to have gearbox because the machine is already slow. So gearbox is a thing that's mechanical engineers use to reduce speed. It's called the speed reducers. So usually here if you have 1000 RPM, here maybe with 10 RPM. But for stepper, you don't need that. So you can save cost in solar tracker applications. A wide range of rotational speeds can be realized as the speed is proportional to the frequency of the input pulses. You can have the 4 windings fired at the same time, and then you.
دكتور الروتيشن ما راح تكون سموث صح؟
No, it's not smooth. It's a step in step. Move and stop.
ما تقدر يعني تخليها سموث.
Well, it's not designed for that. To get a smooth rotation, you need our favorite animal. What's our favorite animal? RMF. You need rotating magnetic field. You need this in blue to rotate as function of time. 60 hertz 50 hertz whatever.
بس دكتور لما تشوف السولار بانل زي تشوفها سموث لما تتحرك.
step angle small.
ممكن.
Yeah, some of them يعني during the operation in the morning they go on tilt. Some of them are like that. It is okay. I'm not saying it's you just send very fast power electronics. But from 1 p.m. to 1:05 p.m. the sun is going a little bit down, so that movement is very slow. You don't see it by eyes. But if you're talking about maintenance, they want to make the solar panels flat, stow position we call it. The stow position, yeah, maybe you can send one central command and have, actually, you can have it 90 degrees by having the correct pulses, skip all the other pulses using pulse. So you can make it fast, it will be very fast movement. From here to 90 degrees, you just energize. I'll explain it and then you will get an idea how to do it for solar. Tamam? The bad stuff, we have resonance. Do you remember resonance? Ranin. Resonance occurs in RLC circuits. Resonance can occur and they might freeze. Not easy to operate at very high speed. Very high speed is not easy. It's doable, but it's not easy. What are the types of stepper machines, stepper motor? The first one we talk about is reactive rotor. It's variable reluctance, VR. They're not virtual reality. You know virtual reality? VR is variable reluctance. The other one is active rotor, where there is a permanent magnet. Some of them, they have permanent magnet. The last type is the hybrid. Is it hybrid car? No, it is hybrid of VR plus PM. This is another design. What are the applications? Printers, graph plotters, tape drivers, disk drivers, if you have CDs or something like that, machine tools, XY recorders, robotic space vehicle, this is in the space they use stepper motor, and electric watches. Some mechanical watches, they don't have a machine, they use speed reducers. So let's talk about the first type, which is called the variable reactance. The VR stepper motor characterized by the fact that there is no permanent magnet. That's a key characteristic, no permanent magnet on either rotor or stator. For this figure 1, how many poles do I have on the stator? 4. And how many poles in the rotor? 1. Not 1. We don't have 1 pole. We're not UK. 2. 1, 2. For this machine, how many poles in the stator? 6. In the rotor?
4.
So now you just say 6 to 4. 6 to 4 VR. Clear? It's very important to understand the geometry of them, because when you create the control tables for your machines, it will be, the number of rows will be based on the number of stator poles. How does it work? Well, this is very important. Flux lines prefer moving in a smaller reluctance. Flux lines do not like moving through the air. Flux lines would pull the head of this rotor here so that they can move in steel. The way it works is they would start moving here and over time they would shift it. Get it?
Doctor, what about the 4 poles?
I'll explain. 4 poles of the stator?
A rotor.
Yeah, I will explain it. 4 poles, then it means you will have power electronics that's more advanced. But let's think of it as a little bit. Flux lines prefer to be short as possible. The rotor moves until being face to face with the stator pole. They have to be face to face. They have to have face to face. The other thing here is this equation. The equation of full step, we'll explain full step first and then half step later, is a 360 times number of stator poles minus number of rotor poles over the multiplication. So for this application, 360 times 6 minus 4, 2, over 6 times 4, 24. So 360 times 1 over 12 is 30 degrees. So this is stepper motor. If you do full rotation, it will rotate 30 degrees from 360 of the stator mechanical degrees. I will explain the power electronics. Here, this is what I'm talking about. Here, how many you have? 4. So here you have 4. It means you have to have 4 positions. 4 positions. To make a complete rotation, you need to have 4 pulses by the power electronics. At standstill, reference 0, coil 1 is energized. Coils 2 and 3, they don't have energy. They're green. Red is hot. Did I tell you the red is hot joke or not yet? Okay, I will conclude with red of hot. If you go in the field, they usually with the breakers, if it's active, they put red tag. So always red is hot. And who taught me this? A technician with a company. Red is hot. So in your simulation, never ever have a green hot breaker. This is like an open. Okay? So the joke is red is hot. That's it. It's not a joke, it's more like a fact. Okay? Red is hot. If you go and you see a breaker, if you see a red tag, it means red is hot, it means do not touch it. Actually, you are not allowed as an engineer to touch it. Do coil 2, I'll do only one coil and then we'll go. Make 1 and 3 de-energized, energize 2, what will happen? Either this or that. Which one is closer? هذا ولا هذا? A or B? No, A. A is closer to 2. So if you energize 2, no, because A is closer, B will be aligned. هذا will be aligned here if you energize 2. Now you moved how many degrees? 30 degrees. How to move another 30 degrees? Make coil 3 active. And then the B will be here, the A will be here. So A will rotate. And then you change the pulses. Okay, what if I want to move only 15 degrees? What will happen if I keep 1 energized and energize 2 at the same time? The angle will be similar to the half rotation, and it will be only 15 degrees if it's 110. This is how stepper motor would work. With that, we'll start next lecture here, okay? Please make sure to study. Quiz, fake quiz.